this chapter titled Stress and Deformation Analysis. It's to a good extent a review of strengths of materials, and it introduces a couple of new concepts. First being curved beams, the other one being on principal superposition, and we'll then have some, or do some problems in a different recording. I'm going to use an overhead camera. Okay, so again, most of it is review. We looked at it. Emphasis now being on more on machines rather than structures. Combination of machines and structures, like you had it in strengths of materials. So this is pure mechanical engineering stuff versus some civil engineering from the strengths book. Okay, so essential to be proficient in free body diagram and static load analysis of statically determined systems. There are a number of sample problems. We looked very briefly at this one. So loading for this crane happens in the vertical plane, and we assume the base to be fixed to the ground, and we're interested in stresses in the various elements. We recognize that strut 1 and brace 2 are two force members. It means that the reaction forces are aligned with FD line and C and a point that's not labeled here. We assume that they are pinned rather than welded, although we'd expect these to be weld ones, but in order to have this a true, or the individual elements to be statically determined, we are assuming them to be pinned together. And firstly, you do a static analysis of the entire unit to find the reactions at the mounts A and D, and you're going to some moments about A, right? Moment equilibrium equation. That'll get you the reaction at B, and then you some moments about B gets you the reaction at A. At A, we know direction of the reaction. Again, this is a two-force member, clearly. Resultant or reaction at A, it's in line with AC. So they moved. A now occurs here versus a slight change over the original image. All right, and then you do free body diagrams, draw free body diagrams of the individual links. External load known. We have the reaction of the supports known. If you're to, an alternative is just to do free body diagram of the links and write equilibrium equation starting with the loaded, the boom link number 3, and you know the direction of reaction at F. Again, summing moments about point E, point F, and then there's equilibrium in the force equilibrium X and Y direction, and there'll be enough information to calculate the reactions. And then you move forward. Two force member, clearly this force is transmitted to point D, and these are present here but flipped sign, and so forth. Again, proficiency with static analysis is paramount. If you have issues with statics, then you will continue having issues with in this class to a good extent, which is unfortunate. Okay. And then for stress analysis, everybody knows drawing, or of, hopefully everybody knows drawing shear force and bending moment diagrams. I said everybody knows of them. And you're looking for the maximum bending moment to calculate the stresses. So for this case, with negative bending, we're having a maximum tensile on top and maximum compressive below. Using flexure formula and knowledge about the cross-section allows us to find the maximum stress. Okay, so there's a summary of what is discussed in this chapter. We looked at stresses, rather stress elements, and these are principal stresses. When you don't see this is principal stress, this is principal stress element. When you don't see shear, it means that it's the case of a principal element. We'll discuss more in chapter 4 about that. All right, so tension in the x direction, compression in the y direction, pure shear, and the sign convention is when the shear stress tends to rotate the element in the counterclockwise direction. That's assumed to be a positive shear, and when it tends to rotate the element in clockwise direction, that's assumed to be convention. Sign convention for the shear stress is that it is a negative shear stress. Things about units, the case, and we know these from strength of materials. This is a specimen in tension. The axial load stress element. For convenience, we align it with the element is aligned with the axis. The stress element at A, it's aligned with the axis of the part. Okay, in order to have an instance like this one or a 2D view, as you can see here, and Hooke's law allows us to calculate deformation by expliciting the strain delta. Okay, so delta is going to be F times L over A over E. So remember, if you're putting this in Excel, you need to have E times A in parentheses. Otherwise, the results will be wrong. Or you can also use sigma, that is the stress. So working with, this is sigma, so it'll be delta is sigma times L over E, a second form for the strain calculation in direct tension or compression. When we have shear loading, the stress is calculated as the force over shear area. Shear loading, for example, occurs when you shear pins, either simple double shear, go back to the strength book, or keys in machine elements. So the shear plane would be the interface plane between the shaft and the hub. We know the geometry of the key, so this here is the shear area. We can calculate the force by knowing that, knowing that the torque transmitted, something that should come from early analysis. Torque transmitted is force times radius of the shaft, or inner radius of the inner or the bore on the hub, and we calculate this way the shear stress, and then in torsion, many machine elements are loaded with torques as they transmit power, and we know the stress distribution in when shaft is twisted, and it's linear, going from 0 to the neutral axis, the center of the shaft, to maximum on the outside, and this vector is again the maximum shear stress, and these vectors can be assumed like an array of them in any direction. Again, maximum stress occurs on the outer skin, and it has this magnitude. So torque transmitted, C is essentially the outer diameter divided by 2, and this is polar moment of inertia for a solid round bar. It's pi diameter power 4 over 32. Okay. Maximum shear stress, knowledge of it allows us to check and see if the material can sustain the torque without permanent deformation. At any radius along the shaft, this is the equation to use. You replace C with R. Now, for convenience, we want, or we'll be using, instead of polar moment of inertia, polar section modulus, which you get it by dividing polar moment of inertia by diameter divided by 2. This is listed with cross sections that is solid, round, or tubular, and it's easier to use in calculations, particularly for tubular parts, because here you have a combination of outer diameter, inner diameter, and you can get the same polar moment of inertia with different combinations of capital D and lowercase d, that is outer diameter, inner diameter. Here, stress distribution is also linear, maximum to the outer skin, same as before. And equation to use to calculate maximum shear stress caused by torsion is torque times C, which is capital D divided by 2, and polar moment of inertia has this form. Torsional deformation, the deflection of the small pieces of material throughout the shaft, knowing the length between the two sections that we want to calculate the angle of rotation. Relative angle of rotation could be the end of the shaft or could be in between. I can delimit the portion that I want to analyze for twist, for the angle of twist. So in radians is going to be torque times length. Length would be distance from here to here, for example, and divided by modulus of elasticity of material and shear. You can calculate it based on Poisson ratio and on the Young's modulus. There's a relationship that combines E, Young's modulus, G, modulus of elasticity and shear, and Poisson ratio, and this would be the polar moment of inertia. Likewise, this should be in parentheses. Put this equation in Excel without parentheses, you get wrong answers. If we have non-circular cross sections, there are ways of calculating maximum shear stress as well as the angle of twist in radians, using these two equations. Again, this is in parentheses, where this coefficient Q and K for angle of twist in radians, you get them from a table like this. Maximum stress occurs, as you can see, at where these dots are shown, and just study the table, with the information provided, calculate the two coefficients, and then simply apply equation 312 and 313. If we have, in general, a closed thin wall tubing, you can calculate the two coefficients using the perimeter of the medium boundary, length of the medium boundary, and the area delimited by the medium boundary, and then there's the is the thickness of the material used to form this thin wall tubing. Using the last entry in this table on figure 310, we can calculate the maximum shear stress and angle of twist, and it's an exercise here where the two are compares angle of twist for a ring and for a split tubing, that is a tubing and a split tubing, say form of sheet metal but not welded, and this is detailed here for the given geometry, and it shows that the angle of twist is it's 345 bigger for the split tubing, and the stress goes up 31.1 times versus the welded tubing, quite substantial. Now bending causes shear stresses, and if you remember, actually not remember, will be discussed later in when designing shafts. So at the supports, bending moment it's very small, but and the maximum or stresses that occur are due to the shear caused by bending. And you look at the shear diagram that is paired with the bending moment diagram not listed here, and you can analyze or calculate the shear stresses caused by bending. And we can perform analysis on any longitudinal plane. So this is a transverse cross section. This is the neutral axis at any location along the cross section using this general formula. So shear at this location is going to be the shear force from the shear diagram, and then we have first moment of area as defined here divided by area moment of inertia of the entire cross section divided by the thickness at the cross section where we calculate the stress. Okay, and the first moment of area, you get it by taking the area either above or below times the distance from the neutral axis to the centroid, of the cross section above the line. I think I'm so here the way it's shown is like calculating the shear. So with the crosshatch, essentially it's calculating the shear stress at the neutral axis. Okay, so y would be for this rectangular cross section would be h divided by 4. So area P is going to be area of this rectangle. Distance from the neutral axis to the centroid of the area above is going to be h divided by 4. But we can analyze for stress any line that is, and again I listed or indicated at first that this is the section that we are interested in. Really, the drawing is for calculating the shear caused by bending at the neutral axis, which happens to be in most practical cross sections the maximum. The good thing, because maximum stress caused by bending, it's on the outer skin. This is where the bending moment is 0. Okay, so here's the Serres-Shibura. It was the maximum value calculated as explained here and in the text. There are here shows the stress element aligned with the beam. So shear stresses are always grouped in pairs. The element force-wise is in equilibrium. The effect of shear stress is the formation of the element. So it changes from a small square to a diamond. The way it's shown here, the element after deformation will be like so. Okay, diamond that it's tilting to the left, and that angle, change in angle, what was originally 90 degrees, that change in angle from 90 degrees is the actual shear strain, which is measured in radians. Again, go back to your strength book. We have special equations. Spatial formula allows us to calculate maximum shear stress. So on rectangle, circle, I-shaped, thin wall tubing, again, they come from the book, same author, strength book, you know, we'll be using these in search for the maximum shear stresses caused by bending. Okay, bending stresses. The well-known flexure formula allows us to calculate the maximum stress caused by bending anywhere we know M coming from the bending moment diagram. And for a loading like this that shows like a beam or a deck, maybe supported ends, and you have a load right where in between the supports, and it causes the beam to bend downwards. So we'll have compression on top, tension below. A positive moment is going to be associated with compressive stresses above the neutral axis, tensile stresses below the neutral axis. Their magnitude you calculate with, again, flexion formula, M times C, C being the distance from the neutral axis to the outer skin. Could be the same for symmetric cross sections. If it's a T section, there will be a different C. For example, for a T section, there's different C value for above and below the neutral axis. Okay, so look at the orientation of the stresses. Towards the cross section means compression. Away from cross section means tension. Some books assume this line to extend, and it shows the, or rather this way, and it shows the lines going this way, or could be, anyway, a direction of the arrows is, or indicate whether it's tension or compression. Away from the section, tension; towards the section, compression. So on top, where's compression? This is how the principal element, an element aligned with the longitudinal axis of the beam, will look like. Below, stresses away from the surfaces of the small element, and that's tension. Okay. There are some assumptions required in order to apply correctly flexion formula. So it's stress caused by bending. Now it can be associated with other stresses, direct tension or compression, axial stress, axial loading of the beam. That's possible. We'll learn about principle of superposition. But for the stress caused by just bending, and in order for this equation to apply, we need to have no twisting or axial loading, material to be deformed within the elastic range, and that is Hooke's law to apply. The Young's modulus to be the same in tension compression, and no significant change of curvature, so straight or very slightly curved the beam has to be, and loading has to remain in one plane. Offset loading can cause twisting, and no buckling or wrinkling, possibly for I-beams. You know, slender, thin web I-beam can wrinkle under loading. Same as with torsional stresses, bending calculations, particularly sizing beams, it's more convenient if we instead use section modulus S. So you take the area moment of inertia of the cross section and divide it by distance to the outer skin, so area moment of inertia about the x-axis, and you divide it with this distance from the centroid to the outer skin, it gets you the section modulus. This is listed with various sections at the end of the book, and you're going through them. Once you say you select the material, you know the material properties, you want to choose the cross section that limits the stress to a certain maximum value. So flexion formula now becomes, with this definition, it becomes M over S. Okay, and we can, like I said, we can, given the design stress, the applied moment, we can calculate the minimum required section modulus. And this is where it's convenient to use again when instead of again juggling with what, two parameters I and C, as they occur in the original flexure form. Okay. Beams with concentrated bending moments, they were barely touched in the strength book. Now they're discussed more. We have machine elements that may have either induced or directly applied moments. We're going to come back to this problem, assuming it to be a pressurized pipe, once we discuss from the book, the strength book, the pressure vessels, and it's a matter of analyzing this section ABC, the effect of this L piece that is jointed, welded at point B, is of a moment that it's in the XZ plane acting the way it's shown. So it's going this way. If you follow the mouse cursor, it goes this way. It is the load diagram with reactions at A and C, and the load, the 60-pound force is delivered here, or in a free body diagram. When you take this off, the effect of this L piece is a down force in this moment M. M calculated 60 times arm of 3 inches, 180 pound inch. Okay. There is a sign convention when it comes to concentrating bend moments. So if the bending moment is in counterclockwise direction, like shown here, the moment diagram drops, as you can see. If we reverse it, if instead this force is pushing up, then it will be a rise in the bending moment diagram. So this is the effect of concentrated moment. You analyze them, draw the shear diagram. It's not affected by M. But when it comes to moment, you need to take care of these drops or jumps in the bending moment on the M diagram. As usual, we're after the maximum bending moment to calculate the maximum stresses caused by bending. And again, feel free to study the chapter, read the sample problems, also from the strength book, borrowed here. Just FYI, no accompanying charts to select the flexure moment. So we want to, when we load the beam, in order to avoid any twisting which causes additional stresses, we want the force to be, if the cross-section is symmetric, the force to go through the centroid. Okay, so all these have symmetry, and the median vertical plane should be the load plane in order not to induce any twisting, any torsional stress. If, however, we have sections that are not symmetric relative to the loading, there is a what's called flexure center, and you need to fabricate brackets that will offset the force to where the force plane go through the flexure center to eliminate the possibility of twisting the section. So an angle equal wing angle iron. This is the centroid. Flexure center is offset, as you can see. If it's a hat section, about similar to the C channel loaded on the side, it has to be offset by some amount. And again, go back to the strength book to where this is detailed. Calculation of beam deflection, as well as angle of bending angle. So there are machine elements carrying gears, so gear transmissions on with gear pairs on shafts. They tend, in mesh gears, tend to separate themselves. There are forces that are oriented towards the center of the shaft or axis of the shaft and cause the, for example, this is a 3D view, this is a side view. This shaft is going to be loaded with one force pointing down and another force pointing down. The shaft is going to bend depending on the magnitude of these forces, as well as its stiffness, this material, and Young's modulus area moment of inertia of the shaft material. And here's an example again for the one gear only carrying shafts, these two, and two gear carrying shafts, and it shows forces tend to repel the two gears. You can see they're away from each other, and the shaft deflects. And we like to know how much this deflection has to be limited. The book lists the amount of linear deflection on shafts. With deflection comes change of slope. So if you have a gear, there's also, the book does not discuss this, but as the shaft deflects, the gear will follow locally and will align itself with the tangent. The gear will align itself with the tangent. I should point to this one, with the tangent at that location on the shaft, and they not just repel themselves in plane, but they also can rotate relative to each other, and that may cause meshing on the side of the tooth rather than on the full width, and that's further detrimental to the operation of the gear transmission. So how do we calculate the amount of deflection of the shaft? We can use successive integration discussed in strength of materials. So the beam equation, moment over stiffness along the beam, and this could change by changing the diameter. Say if you have a stepped shaft, I changes with location. If it's and majority of cases, of course, we have the same material, but cross section can change, and area moment of inertia can change, equals the second derivative of the deflection of the shaft. So I'm looking for a reference frame. Y is measured, X is longitudinal to the beam or shaft, and Y is transverse deflection. And we have these relationships. Equation of the neutral axis, a function of X. Its derivative is going to be the slope in radians at the point of interest. So again, we have curvature. There is a slope which changes when maximum deflection. Slope is 0. Depending on the support, here simply supported, so we have possibility of rotation of the shaft. Cantilevers are different. There's no initial condition, is like no slope and no deflection at the support, assuming you have an incastration here, free end here. And again, successive integration, it's like going in reverse. So we're looking at these equations. We have the relationship between the moment diagram and second derivative of the deflection follows this equation. Third derivative of the deflected neutral axis is equal to the shear force divided by beam stiffness. E times I is beam stiffness at the location. And if we have distributed force, then force derivative of the deflected neutral axis is going to give you distributed force, which can have any, in general, could be any shape, could be linearly varying, could be parabolic, or constant. So force derivative of the neutral axis is the one that's it's given us the distributed load divided by beam stiffness. Using these equations are useful when we have different moments of inertia along the beam. So you have a step shaft, for example. This is where you could, it's where we resort to these equations, calculate the maximum deflection at certain locations on the beam. Otherwise, there are equations, the back of the book in the strengths book, that allows us to calculate either using directly the equations or using principal superpositions to calculate the deflection at certain locations. So successive integration, there are constants of integration that we need to reconcile or determine, and they are based on the end supports again. So for a simply supported beam, I want to have the deflection of both ends equal 0. If I integrate from left to right, as it's usually the case, I know that deflection y at x equals 0 is going to be 0. Deflection y at x equals length of the beam is going to be also 0. Slope theta is not going to be 0, and will result from integration. If I have a cantilever, I know that at the incastration both y and theta are 0. Those are easier cases with cantilevers to do successful integration, is because I immediately know what the constant of integrations, these two will be both 0 for an incastrated beam. Okay, curved beam. This is new material. So I'm looking. It's minute 37. This is where the review stops and the new material begins. Curved beams. Curved beams. You see them in mechanical engineering practice on frames of machine, like Oakham frames, machine presses, seat clamps, milling machines, bodies, say, here lists, so automotive frames, suspension elements, so a good number of applications, tools like pliers or plier handles, and we want to know what the stress is. The flexure formula is no longer correct. The linear distribution of stresses that you see on straight beam bending of straight beams is no longer applicable here. The analysis, you'll see, is based on a figure like this one. The cross section is rectangular for this case. The neutral axis is a geometric axis. Neutral axis or centroidal axis is the geometric center, but the axis of 0 stress caused by bending will be offset to the inside of the curvature of the curved beam. We have moments that here tend to straighten the beam. So there is a sign convention. So if the moment tends to straighten, so make the beam straight, or reduce its amount of bending, that is, increase the curvature, the radius of curvature, then this is considered positive. And when the moment applied wants to further bend the beam, that is, decrease the radius of curvature, is considered to be negative. This is essential. You need to identify or establish whether the moment is negative or positive to correctly apply some equation that will be discussed in just a little bit. The section, the stress distribution in the cross section is no longer linear, rather has this parabolic shape. Same as with straight beams, we had if the bending is positive, I have compression on top, tension below. There is on this figure there is a capital R that it's not exactly drawn here, but this R is through the neutral axis, the curved beam, and it goes from inner radius to outer radius. This is a current radius, or that could be a current radius, but RC is through the centroid. Okay, not shown here, or is it? Or no explanation of what R is, but really R is a generic radius anywhere between R1 and RI, internal radius and outer radius. And without any proof, we're provided with equations allows us to calculate the stress distribution across the cross section of the C or the curved beam, and will be the bending moment from other analysis of the problem. So it could be caused by a force, and here's the R, capital R, that positions the neutral axis. We'll see how it's calculated. And then RC is centroidal radius, and then we have current radius R, which could be either RC or RO if we're to calculate a maximum compressive or maximum tensile stresses. Okay, and A is the area of the cross section. For rectangle, will be just B times H. Okay. How do we calculate R? We calculate using what is called area shape factor. So you divide by area of the cross section by this area shape factor, and the area shape factor, we have a number of common cross sections, as well as it's explained how do you tackle problems where you have combination of shapes. So you need to read carefully, orient the cross section for your problem. Identify what RI, that is internal radius, outer radius, as well as the radius through the centroid of the cross section R, and area is simple. It's going to just be B times H. But area shape factor, you can see here, it's a natural logarithm occurs. So it's going to be B times outer radius divided by inner radius. So area shape factor for a rectangular cross section. It's a triangle. We have area, everybody knows, formula for area of a triangle. Area shape factor, also a natural logarithm occurs and uses outer radius, again inner radius, as well as B. Okay, that is the width of the base. For a solid round bar that is bent, area shape factor, area is easy, pi diameter square over 4. Area shape factor, as you can see, it's using the radius through the geometric center. If it's an elliptical cross section, trapezoidal inverted T section, uneven I beam. If it's half a round, either bend this way or clearly the center of curvature of the bend is to the, so both are bent towards the again, this is the transverse section. So we get the area would be half the area of a disc, and then area shape factor, different equations depending on how they compare the inner radius of bent to the diameter of the semicircle. Okay. So again, it's in applying the equation that was introduced for shear stress, it's essential to identify the sign plus or minus of the moment. You calculate R using area shape factors. The steps are listed here. I modified them some because you go in this succession. Calculate the area. So find M. Do necessary analysis, static force analysis, moment analysis. You find the centroid of the section, find the inner radius, outer radius area to the centroid, and you calculate R using the equation 27, this one here, based on the compute the area shape factor for the cross section. Stress to the outer side and the inside, the maximum stresses again occur on the outside, inside of the bend. You just make R either RE for the inside stress or RO for the outer stress, and this equation repeat it here for R equals R0 and R equals rather RO and R equals RE to the inside. Okay. If we have combination of shapes, say you have a rectangle with that has welded at the end of one of these half discs, or not welded, could be a rectangle piece that is rounded. Okay, looks like a field track. Then the book explains how we were dealing with it. The equations are the same to calculate the stress at the outside or the inside. What is different is the radius to the neutral axis, and you divide the total area by the sum of area shape factors of the individual or the component simple shape. So yeah, a trapezoid that is filleted, or we have a trapezoid with two rectangles. Area in this equation is going to be total area, easy, and then area shape factors, you're just assuming half a disc, another half a disc, the trapezoid itself, or trapezoid with two rectangular pieces. Calculate the area shape factor for each. You take the sum of the three and use it to divide the total area, and it gets you R, which occurs in this formula. So not very complicated. Again, the difficulty may be in the calculating the moment correct way, and also telling whether it's observing its sign, whether it's positive or negative. So as shown here, this is a negative moment because it tends to further increase the radius of curvature of the beam. One way of verifying the correctness of calculations is just looking at the signs of these outer stress and inner stress. So the outer stress for using the two equations. So you calculate the outer stress, the inner stress. So if for whatever sign you assume for the moment, you look at the actual figure. So a negative bending moment of the curved beam should give you a positive stress on the outside and a compressive stress that is negative to the inside. If moment is positive, like in the earlier figure, like this one, or let's look at the very first one. So as shown here, the moment is positive and it's going to give you negative outer stress, maximum outer stress, and positive inner stress at Ri. So negative at Ro and positive at Ri, the two equations. But best is if you start with the correct assumptions, you do the analysis the right way, see whether it has a tendency to straighten the beam or further increase its bend, reduce the radius of curvature, and one would be positive, the other negative. So not very complicated, I would say. The book continues. The book continues with, or the chapter, taking the cases of overlapping and before that? Is there discuss the stress concentration? Stress. Okay. The alternative approach is this. Other sources, other books, they use. They consider curve beam like having stress concentrators. I'm familiar with one of those books, and they use charts to get you a coefficient, an equivalent to stress concentration factor from where we extracted. Sorry for the. Looks like I'm receiving emails. Let me take a break and see who's writing. Might be students. Right. So we stopped discussing the chapter here at superposition principle. Is it possible to have, in addition to bending, other effects like axial, tensile, compressive forces? And these are easy to handle cases we'll discuss later on, chapter 4, how to calculate equivalent stresses and principal stresses when you have a combination of bending and torsion, or axial load and torsion, but really for what is discussed here, it's just a matter of overlapping stress distribution, assuming the bending happening independent of the axial load. So, for example, for curved beams, you can have the bending moment being caused by an applied force. So, force applied with some eccentricity that causes the moment, but there's also the force itself that causes a stress, and that will have the distribution in line with that caused by bending, and you just overlap the two stress profiles. An example in the book to illustrate this principle is this of a cantilever beam encastrated at this end, and we have a force F acting at an angle and eccentric from the centroidal axis. You can see here it's an I beam. So what the force does is causes bending, and then it causes axial loading. So we have, due to the eccentricity E, we have a moment that is acting counterclockwise, and it's shown here. It's equal to the horizontal component of the force times eccentricity E. So that's the acts like a concentrated moment end of the beam. We have axial force equals to the x component of the force, assuming or in line with the centroidal axis. And then we have a down force that causes bending the way we know it. So imagine a encastrated cantilever beam with a down force that also has this bending moment acting counterclockwise, as well as the concentrated moment applied acting counterclockwise, and the axial force. Static equilibrium gives us reactions at the encastration, and with it we can draw a shear force and bending moment diagram, and see the bending moment diagram ends, since we have a moment, concentrated moment at the end of the beam, ends like non-zero. So this would be the value of the moment. And in terms of their effect, less the axial force, we have maximum bending stress occurring at the incastration. See their distribution. So the down force Fy causes more negative bending than the positive bending of M2, and then on top of it we are adding the tensile force. So maximum moment of the incastration divided by section modulus of the I-beam provided. You calculate the maximum tensile, maximum compressive force, and this is overlapped with the effect of the tension by force Fx, and the resultant stress distribution is increase in maximum tensile stress and reduction in the same amount but reduction of the compressive stress. And as you can see, so tensile stress went up, compressive stress went down, and you could use this to calculate the design factor, or well, the beam was assumed given to calculate design factor given the material available for the beam. Stress concentration, this is subject from strengths of materials you're familiar with. You know, when we have transition in the cross section of beams or shafts, there's localized increase of stress, and experimentally with or numerically these have been calculated and tabulated in the form of charts, parametric charts. Some excerpts of what's available at the back of the book. So this would be for direct tension, a plate of thickness T, change in width, the way it's shown, and looks like there's a typo here, so this will be capital H, and this is lowercase h. Bending of a round shaft with a step. You need to know field radius. Again, read carefully. The nominal stress value is given here, and likewise, and you're just calculating a stress concentration factor that multiplies the nominal stress. Here is tension of a plate with a hole. Here's torsion of a round solid shaft with a hole. They are also the back of the book listed. The one that's not available at the back of the book would be the case of a stress concentration occurring where we have a load applied to a plate via a pin, like in this kind of clevis assembly, or this is the pin lock connection. All right, so this is the only place where it's available. Look at how the nominal stress is calculated. It takes as a transverse area the minimum area, that is original section minus the projected area of the hull, and depending on a ratio of hole to width, you can find the stress concentrator that multiply the nominal stress. Okay, again, this is not available at the back of the book, and was not discussed, I believe, in the strength book. Okay, so this will be it for now. I'm going to issue a list of recommended problems, my way of guiding students through the application part of each chapter, and we're going to do some of the selected problems with emphasis on the new material. Okay, so I'm stopping the recording, and we'll do the overhead camera, some exercises, pen and paper.